spring.data.cassandra.contact-points property is where you identify the host name or names of Cassandra. A contact point is the host where a Cassandra node is running. By default, it's set to localhost, but you can set it to a list of host names. It will try each contact point until it's able to connect to one. This is to ensure that there's no single point of failure in the Cassandra cluster, and that the application will be able to connect with the cluster through one of the given contact points. You may also need to specify a username and password for your Cassandra cluster. This can be done by setting the spring.data.cassandra.username and spring.data.cassandra.password properties as shown next. These are the only properties you'll need for working with a locally running Cassandra database. In addition to these two properties, however, you may wish to set others, depending on how you've configured your Cassandra cluster. Now that Spring Data Cassandra is enabled and configured in your project, you're almost ready to map your domain types to Cassandra tables and write repositories. But first, let's step back and consider a few basic points of Cassandra data modeling. Section 4.1.2 Understanding Cassandra Data Modeling. As I mentioned, Cassandra is quite different from a relational database. Before you can start mapping your domain types to Cassandra tables, it's important to understand a few of the ways that Cassandra data modeling is different from how you might model your data for persistence in a relational database. A few of the most important things to understand about Cassandra data modeling follow. Cassandra tables may have any number of columns, but not all rows will necessarily use all of those columns. Cassandra databases are split across multiple partitions. Any row in a given table may be managed by one or more partitions, but it's unlikely that all partitions will have all rows. A Cassandra table has two kinds of keys, partition keys and clustering keys. Hash operations are performed on each row's partition key to determine which partition or partitions that row will be managed by. Clustering keys determine the order in which the rows are maintained within a partition, not necessarily the order in which they may appear in the results of a query. Refer to Cassandra documentation, see this link, for a more detailed explanation of data modeling in Cassandra, including partitions, clusters, and their respective keys. Cassandra is highly optimized for read operations. As such, it's common and desirable for tables to be highly denormalized and for data to be duplicated across multiple tables. For example, customer information may be kept in a customer table, as well as duplicated in a table containing orders placed by customers. Suffice it to say that adapting the Taco Cloud domain types to work with Cassandra won't be a matter of simply swapping out a few JPA annotations for Cassandra annotations. You'll have to rethink how you modeled the data. Section 4.1.3 Mapping Domain Types for Cassandra Persistence. In Chapter 3, you marked up your domain types, taco, ingredient, taco order, and so on, with annotations provided by the JPA specification. These annotations mapped your domain types as entities to be persisted to a relational database. Although those annotations won't work for Cassandra persistence, Spring Data Cassandra provides its own set of mapping annotations for a similar purpose. Let's start with the ingredient class, because it's the simplest to map for Cassandra. The new Cassandra-ready ingredient class looks like this. The ingredient class seems to contradict everything I said about just swapping out a few annotations. Rather than annotating the class with @entity, as you did for JPA persistence, it's annotated with @table to indicate that ingredients should be persisted to a table named ingredients. And rather than annotate the ID property with @ID, this time it's annotated with @primary key. So far, it seems that you're only swapping out a few annotations. But don't let the ingredient mapping fool you. The ingredient class is one of your simplest domain types. Things get more interesting when you map the taco class for Cassandra persistence, as shown in the next listing. As you can see, mapping the taco class is a bit more involved. As with ingredient, the @table annotation is used to identify tacos as the name of the table that tacos should be written to. But that's the only thing similar to ingredient. The ID property is still your primary key, but it's only one of two primary key columns. More specifically, the ID property is annotated with @PrimaryKeyColumn with a type of primary key type.partitioned. This specifies that the ID property serves as the partition key, used to determine to which Cassandra partition or partitions each row of Taco data will be written. You'll also notice that the ID property is now a UUID instead of a long. Although it's not required, properties that hold a generated ID value are commonly of type UUID. Moreover, the UUID is initialized with a time-based UUID value for new Taco objects, but which may be overridden when reading an existing Taco from the database. A little further down, you see the create@ property that's mapped as another primary key column. But in this case, the type attribute of @PrimaryKeyColumn is set to PrimaryKeyType.clustered, which designates the create@ property as a clustering key. As mentioned earlier, clustering keys are used to determine the ordering of rows within a partition. More specifically, the ordering is set to descending order. Therefore, within a given partition, newer rows appear first in the tacos table. Finally, the ingredients property is now a list of ingredient UDT objects instead of a list of ingredient objects. As you'll recall, Cassandra tables are highly denormalized and may contain data that's duplicated from other tables. Although the ingredient table will serve as the table of record for all available ingredients, the ingredients chosen for a taco will be duplicated in the ingredients column. Rather than simply reference one or more rows in the ingredients table, the ingredients property will contain full data for each chosen ingredient. But why do you need to introduce a new ingredient UDT class? Why can't you just reuse the ingredient class? Put simply, columns that contain collections of data, such as the ingredients column, must be collections of native types, integers, strings, and so on, or user-defined types. In Cassandra, user-defined types enable you to declare table columns that are richer than simple native types. Often they're used as a denormalized analog for relational foreign keys. In contrast to foreign keys, which only hold a reference to a row in another table, columns with user-defined types actually carry data that may be copied from a row in another table. In the case of the ingredients column in the tacos table, it will contain a collection of data structures that define the ingredients themselves. You can't use the ingredient class as a user-defined type because the @table annotation has already mapped it as an entity for persistence in Cassandra. Therefore, you must create a new class to define how ingredients will be stored in the ingredients column of the taco table. Ingredient UDT, where UDT means user-defined type, is the class for the job, as shown here. Although ingredient UDT looks a lot like ingredient, its mapping requirements are much simpler. It's annotated with @user-defined type to identify it as a user-defined type in Cassandra. But otherwise, it's a simple class with a few properties. You'll also note that the ingredient UDT class doesn't include an ID property. Although it could include a copy of the ID property from the source ingredient, that's not necessary. In fact, the user-defined type may include any properties you wish. It doesn't need to be a one-to-one mapping with any table definition. I realize that it might be difficult to visualize how data in a user-defined type relates to data that's persisted to a table. Figure 4.1 shows the data model for the entire Taco Cloud database, including user-defined types. Specific to the user-defined type that you just created, notice how Taco has a list of ingredient UDT objects, which holds data copied from ingredient objects. When a taco is persisted, it's the taco object and the list of ingredient UDT objects that's persisted to the tacos table. The list of ingredient UDT objects is persisted entirely within the ingredients column. Another way of looking at this that might help you understand how user-defined types are used is to query the database for rows from the tacos table. Using CQL and the CQL-SH tool that comes with Cassandra, you see the following results. As you can see, the ID, name, and created@ columns contain simple values. In that regard, They aren't much different than what you'd expect from a similar query against a relational database. But the ingredients column is a little different. Because it's defined as containing a collection of the user-defined ingredient type, defined by ingredient UDT, its value appears as a JSON array filled with JSON objects. You'll likely notice other user-defined types in Figure 4.1. You'll certainly be creating some more as you continue mapping your domain to Cassandra tables, including some that will be used by the taco order class. The next listing shows the taco order class modified for Cassandra persistence. Listing 4.2 purposefully omits many of the properties of taco order that don't lend themselves to a discussion of Cassandra data modeling. What's left are a few properties and mappings similar to how taco was defined. @table is used to map taco order to the orders table, much as @table has been used before. In this case, you are unconcerned with ordering, so the ID property is simply annotated with @primary key, designating it as both a partition key and a clustering key with default ordering. The tacos property is of some interest in that it's a list taco UDT instead of a list of taco objects. The relationship between taco order and taco/taco UDT here is similar to the relationship between taco and ingredient/ingredient UDT. That is, rather than joining data from several rows in a separate table through foreign keys, the orders table will contain all of the pertinent taco data, optimizing the table for quick reads. The taco UDT class is quite similar to the ingredient UDT class, although it does include a collection that references another user-defined type, as follows. Although it would have been nice to reuse the same domain classes you created in Chapter 3, or at most to swap out some JPA annotations for Cassandra annotations, the nature of Cassandra persistence is such that it requires you to rethink how your data is modeled. But now that you've mapped your domain, you're ready to write repositories. Section 4.1.4 Writing Cassandra Repositories. As you saw in Chapter 3, writing a repository with Spring Data involves simply declaring an interface that extends one of Spring Data's base repository interfaces and optionally declaring additional query methods for custom queries. As it turns out, writing Cassandra repositories isn't much different. In fact, there's very little that you'll need to change in the repositories we've already written to make them work for Cassandra persistence. For example, consider the following ingredient repository we created in Chapter 3. By extending CRUD repository as shown here, ingredient repository is ready to persist ingredient objects whose ID property, or in the case of Cassandra, the primary key property, is a string. That's perfect. No changes are needed for ingredient repository. The changes required for order repository are only slightly more involved. Instead of a long parameter, the ID parameter type specified when extending CRUD repository will be changed to UUID as follows. There's a lot of power in Cassandra, and when it's teamed up with Spring Data, you can wield that power in your Spring applications. But let's shift our attention to another database for which Spring Data repository support is available, MongoDB. Section 4.2 Writing MongoDB repositories. MongoDB is another well-known NoSQL database. Whereas Cassandra is a column store database, MongoDB is considered a document database. More specifically, MongoDB stores documents in BSON, binary JSON format, which can be queried for and retrieved in a way that's roughly similar to how you might query for data in any other database. As with Cassandra, it's important to understand that MongoDB isn't a relational database. The way you manage your MongoDB server cluster, as well as how you model your data, requires a different mindset than when working with other kinds of databases. That said, working with MongoDB and Spring Data isn't dramatically different from how you might use Spring Data for working with JPA or Cassandra. You'll annotate your domain classes with annotations that map the domain type to a document structure. And you'll write repository interfaces that very much follow the same programming model as those you've seen for JPA and Cassandra. Before you can do any of that, though, you must enable Spring Data MongoDB in your project. Section 4.2.1 Enabling Spring Data MongoDB. To get started with Spring Data MongoDB, you'll need to add the Spring Data MongoDB starter to the project build. As with Spring Data Cassandra, Spring Data MongoDB has two separate starters to choose from, one reactive and one non-reactive. We'll look at the reactive options for persistence in Chapter 13. For now, add the following dependency to the build to work with the non-reactive MongoDB starter. This dependency is also available from the Spring Initializer by checking the MongoDB checkbox under NoSQL. By adding the starter to the build, auto-configuration will be triggered to enable Spring Data support for writing automatic repository interfaces, such as those you wrote for JPA in Chapter 3 or for Cassandra earlier in this chapter. By default, Spring Data MongoDB assumes that you have a MongoDB server running locally and listening on port 27017. If you have Docker installed on your machine, an easy way to get a MongoDB server running is with the following command line. But for convenience in testing or developing, you can choose to work with an embedded Mongo database instead. To do that, add the following Flapdoodle embedded MongoDB dependency to your build. The Flapdoodle embedded database affords you all of the same convenience of working with an in-memory Mongo database as you'd get with H2 when working with relational data. That is, you won't need to have a separate database running, but all data will be wiped clean when you restart the application. Embedded databases are fine for development and testing, but once you take your application to production, you'll want to be sure you set a few properties to let Spring Data MongoDB know where and how your production Mongo database can be accessed, as shown next. Not all of these properties are required, but they're available to help point Spring Data MongoDB in the right direction in the event that your Mongo database isn't running locally. Breaking it down, here's what each property configures. Spring.data.mongodb.host. The hostname where Mongo is running, default localhost. Spring.data.mongodb.port, the port that the Mongo server is listening on, default 27017. Spring.data.mongodb.username, the username for accessing a secured Mongo database. Spring.data.mongodb.password, the password for accessing a secured Mongo database. Spring.data.mongodb.database, the database name, default test. Now that you have Spring Data MongoDB enabled in your project, you need to annotate your domain objects for persistence as documents in MongoDB. Section 4.2.2 Mapping Domain Types to Documents. Spring Data MongoDB offers a handful of annotations that are useful for mapping domain types to document structures to be persisted in MongoDB. Although Spring Data MongoDB provides a half-dozen annotations for mapping, only the following 4 are useful for most common use cases. @ID designates a property as the document ID from Spring Data Commons. @document declares a domain type as a document to be persisted to MongoDB. @field specifies the field name and optionally the order for storing a property in the persisted document. @transient specifies that a property is not to be persisted. Of those 4 annotations, only the @ID and @document annotations are strictly required. Unless you specify otherwise, properties that aren't annotated with @field or @transient will assume a field name equal to the property name. Applying these annotations to the ingredient class, you get the following. As you can see, you place the @document annotation at the class level to indicate that ingredient is a document entity that can be written to and read from a Mongo database. By default, the collection name, the Mongo analog to a relational database table, is based on the class name, with the first letter lowercase. Because you haven't specified otherwise, ingredient objects will be persisted to a collection named ingredient. But you can change that by setting the collection attribute of @document as follows. You'll also notice that the ID property has been annotated with @ID. This designates the property as being the ID of the persisted document. You can use @id on any property whose type is serializable, including string and long. In this case, you're already using the string-defined ID property as a natural identifier, so there's no need to change it to any other type. So far, so good. But you'll recall from earlier in this chapter that ingredient was the easy domain type to map for Cassandra. The other domain types, such as taco, were a bit more challenging. Let's look at how you can map the taco class to see what surprises it might hold. MongoDB's approach to document persistence lends itself very well to the domain-driven design way of applying persistence at the aggregate root level. Documents in MongoDB tend to be defined as aggregate roots, with members of the aggregate as subdocuments. What that means for Taco Cloud is that because Taco is only ever persisted as a member of the Taco order rooted aggregate, the Taco class doesn't need to be annotated as a @document, nor does it need an @id property. The Taco class can remain clean of any persistence annotations, as shown here. The Taco order class, however, being the root of the aggregate, will need to be annotated with @document and have an @id property as follows. For brevity's sake, I've snipped out the various delivery and credit card fields, but from what's left, it's clear that all you need is @document and @id, as with the other domain types. Notice, however, that the ID property has been changed to be a string, as opposed to a long in the JPA version or a UUID in the Cassandra version. As I said earlier, @id can be applied to any serializable type, but if you choose to use a string property as the ID, you get the benefit of Mongo automatically assigning a value to it when it's saved, assuming that it's null. By choosing string, you get a database-managed ID assignment and needn't worry about setting that property manually. Although there are some more advanced and unusual use cases that require additional mapping, you'll find that for most cases, @document and @id, along with an occasional @field or @transient, are sufficient for MongoDB mapping. They certainly do the job for the Taco Cloud domain types. All that's left is to write the repository interfaces. Section 4.2.3 Writing MongoDB Repository Interfaces. Spring Data MongoDB offers automatic repository support similar to what's provided by the Spring Data JPA and Spring Data Cassandra. You'll start by defining a repository for persisting ingredient objects as documents. As before, you can write ingredient repository to extend CRUD repository, as shown here. Wait a minute. That looks identical to the ingredient repository interface you wrote in section 4.1 for Cassandra. Indeed, it's the same interface with no changes. This highlights one of the benefits of extending CRUD repository. It's more portable across various database types and works equally well for MongoDB as for Cassandra. Moving on to the order repository interface, you can see in the following snippet that it's quite straightforward. Just like ingredient repository, order repository extends CRUD repository to gain the optimizations afforded in its insert methods. Otherwise, there's nothing terribly special about this repository compared to some of the other repositories you've defined thus far. Note, however, that the ID parameter when extending CRUD repository is now string instead of long as for JPA or UUID as for Cassandra. This reflects the change we made in Taco order to support automatic assignment of IDs. In the end, working with Spring Data MongoDB